Now let's discuss what I think of as one of the most important examples in regression. So imagine that my y breaks down into two vectors, a group 1 and a group 2, and my design matrix, which I'm going to call W, which will become clear for reasons later, is equal to a matrix called Z and a vector called X, where X is in m by 1 and Z is in m by 2. And Z looks like this. Z looks like Jn1 and then an n1 vector of zeros, and then an n2 vector of zeros, and then an n1 vector of zeros, and then Jn2. So the Z matrix looks like the two-way ANOVA matrix from previously, but we've appended an X onto it as well, an X vector. So this is the example. If we do least squares with this W, we are interested in fitting models where we have a regression line, but separate intercepts for two groups, right? So the coefficient in front of the X is the common slope, and then the coefficient in front of each Z vector is the intercept for each of the groups. Okay, so we want to minimize y minus W, and I'm not going to call it beta, let me call it gamma, quantity squared, where gamma is equal to mu1, the intercept for group 1, mu2, the intercept for group 2, and beta, the common slope across the two groups. So we can write this as y minus x beta minus z, let me just call it mu as the vector of mu1 and mu2. Okay, so we can write it out like that, and then let's figure out what this works out to be. So let's use our standard trick where we hold beta fixed and we come up with the estimate for mu condition as it depends on beta. Well, if beta is held fixed, that's just a vector, and this is just the two-way ANOVA problem that we discussed previously. Remember that the two-way ANOVA problem the solution worked out to be the mean in group 1 and the mean in group 2. So the estimate for mu1, as it depends on beta, has to be the mean of this vector right here. So that has to be y1 bar, the group 1 mean for the y's, minus x1 bar beta. And then mu2, the mean for group 2, as it depends on beta, has to be y2 bar minus x2 bar times beta. Now if I were to plug those back in for mu1 and mu2 into here and subtract them off from y, what I get is nothing other than the centered versions of y. So I get y1 minus y1 bar times jn1, y2 minus y2 bar times jn2, that vector, minus x minus x1 minus x1 bar, x2 minus x2 bar. I didn't define x1 and x2, but let me just say those are just the group components of x. The x1 is the first n1 measurements of x, and x2 is the n2 latter measurements of x, and that should be times beta. Okay? So, oops, and I shouldn't say equal, it has to be greater than or equal to, because we've plugged in the optimal estimates for mu1 and mu2 for a fixed beta. Well, this is now nothing other than regression to the origin with the group-centered version of y and the group-centered version of x. So we know that the estimate of beta hat, the best beta hat that I can get, has to work out to be the regression to the origin estimate from these data. So that's just summation, let me write it out this way, the double sum of, well, here, probably the easiest way to write it out first is y tilde, the inner product of y tilde and x tilde over the inner product of x tilde with itself, where y tilde is the group-centered version of y, and x tilde is the group-centered version of x. In other words, by group-centered I mean each observation with its group mean subtracted off. And you can show, and I have this in the notes, okay, and you can show, well, let's just do it really quickly here. What does this work out to be? This works out to be the double sum, let's say, over I and j of y I j minus y bar I, so I equal 1 to 2 and j equal 1 to n sub I, x I j minus x bar I, all over the double sum of x I j minus x bar I. And let me just explain my notation here. So y I j is the jth component of, let's say y11 is the first component of the vector y1, y12 is the second component of vector y1, y21 is the first component of vector y2, and so on. So we can write this out, and I think this is probably the nicest way to write it out, as for I equal 1, we can write this out as p times beta 1 hat plus 1 minus p times beta 2 hat, where beta 1 hat is the regression estimate for only group 1. If you only had the x1 and y1 data, the centered x1 data and the centered y1 data, y1 data, and beta 2 hat is the regression estimate if you only had the y2, the centered y2 data and the centered x2 data. Okay, so it is interesting to note that the slope from ANCOVA works out to be an average, a weighted average of the individual group-specific slopes, where in this case p works out to be the summation of xij minus summation of x1j minus x1 bar over sum, and this should have been squared, sorry about that, the double sum of x1j minus x1 bar squared. Okay, so p works out to be the percentage xij minus x bar I. So p works out to be the percentage of the total variation in the x's from group 1. So if most of your variation in your x's is in your group 1, then the group 1 slope contributes more to the overall ANOVA slope, and if the group 2 is more variable, then the group 2 contributes more, and if they're equally variable, then both of them contribute equally. Okay, so let's go back to now, once we have our beta hat, we can figure out what our mu1 hat and our mu2 hat is. So mu1 hat is equal to y1 bar minus x1 bar beta 1 hat, and mu2 hat is equal to y2 bar minus x2 bar beta 2 hat. Okay, so the difference in the means, mu1 hat minus mu2 hat, works out to be y1 bar minus y2 bar minus x1 bar minus x2 bar beta hat. Now, so and one way to think about this, the most common way to think about ANCOVA, is the instance where you want to compare a treatment, say treatment 1 versus treatment 2, but you have some confounding factor that you need to adjust for. Say, for example, you're looking at a weight loss treatment, and your confounding factor is the initial weight of the person. Okay, and so if the initial starting weight of the people receiving the one weight loss treatment is different than the initial weight of the other weight loss treatment, then you'd be worried about just directly comparing the two means. Well, this shows you what, in addition to the two means, you need to subtract off if you model the data as an ANCOVA model. Most interestingly is if you randomize and your randomization is successful in the sense of balancing this unobserved or this observed covariate, the baseline age, then the group 1 average should be pretty close to the group 2 average, so this difference in means should be quite small, so that whether or not you adjust for baseline weight or omit baseline weight from the model and just do straight two-group ANOVA, the estimate should be very similar. However, on the other hand, if you happen to not have had some randomization and have an imbalance so that the average for group 1 is very different from the average for group 2, then the difference between the unadjusted estimate and the adjusted estimate can be quite large. Okay, so that's ANCOVA. That's an important example. I have some more written about it in the notes, but I think you can actually learn a lot about regression and adjustment just by thinking about this one example.